Okay, so that's where we're talking, right? Within these synapses between these two cell types within the cerebellum. What are we talking about? Well, the cerebellum is responsible for coordination of movements. Think throwing a ball and being able to hit a target, or things like people's classic example is riding a bike. Okay, long-term depression. I might have erased some of this here. LTD, or long-term depression, is a type of synaptic plasticity, which is what we're going to talk heavily about next chapter. And so synaptic plasticity refers to a change in synaptic strength. So this is plasticity, aka change in synaptic strength. Right, that's what plasticity means. And it's plasticity where transmission at the synapse is less effective. Becomes less effective, right? So the goal here, or what's going to happen, maybe not the goal, is that you can see that this synapse between the parallel fiber and the Purkinje neuron releases glutamate and causes some depolarization. That depolarization is going to lessen an LTD. Okay, and so we have to talk about how. All right, so I'm going to get rid of this. I'm dealing with less slide here than normal. So what happens? The parallel fiber releases glutamate. So its neurotransmitter is glutamate. Now glutamate can bind AMPA receptors. So maybe you remember, hopefully you remember something about the structure of AMPA receptors, right, which are part of chapter 6. These receptors are ion channels, right? They are ionotropic receptors. That's a good thing to know for the exam. And so what they do is trigger an EPSP. Right? Glutamate, right, is the primary excitatory neurotransmitter, so it's not surprising that they trigger an EPSP, and you can see what happens here, right? These green spheres that I'm now coloring red are released. They bind to the ionotropic receptor for glutamate, which is AMPA, and that causes a depolarization as positively charged sodium enters the cell. All right, that's all well and good, but where's the LTD? Well, at the same time, right, the glutamate that's released also binds to the metabotropic receptors for glutamate, mGluRs, right? These are G-protein coupled receptors. G-protein coupled receptor, okay? And the signaling pathway that this takes is via phospholipase C, right? Phospholipase C leads to production of DAG and IP3. Okay, and so I'm not going to write it out here, but you can see that the mGluR activates PLC, right? And we've talked about this a bunch now, cleaving PIP2, diacylglycerol, inositol triphosphate. And so what happens And the IP3 leads to a small, right? A small release of calcium, and that's important. So some calcium does come in, but that amount is little. So a small amount of calcium is released. At the same time, right? If you look back to our diagram, there's a separate type of fiber called a climbing fiber, right? Right here, climbing fibers. And these climbing fibers are making synaptic connections at the same time as these parallel fibers. So simultaneously. Climbing fibers also release glutamate, and this results in a relatively large increase in intracellular calcium. Right, so this glutamate activates channels, and you can see that channel down here. So the climbing fiber causes depolarization as we activate this calcium channel. So this opens channels to allow in calcium. And this calcium rise is large. So we'll say it to allow in a lot of calcium. Okay, much more than the small amount that was driven by the release from intracellular stores. Okay, so this increase in calcium enhances the sensitivity to the IP3 receptor. So we get even more calcium released. So what we're saying is you can see that calcium signaling that comes in via climbing fiber depolarization, right? It goes two ways, right? It increases, it increases the amount of free calcium, but it also sensitizes the IP3 receptor, right? So now there's even more calcium coming in. Okay, this big change in calcium plus diacylglycerol that's been present from before leads to the activation, finally, of PKC. So the results of high calcium concentration right, plus the diacylglycerol that was liberated before equals, finally, protein kinase C activation. And so an important point here is that this amount of calcium, erase some of this here, right? This initial amount of calcium that's released based on IP3, this calcium is insufficient to activate PKC, right? Calcium levels have to get high enough that require incoming calcium through this climbing fiber mediated depolarization. Okay, so that gives you enough calcium, or gives the Purkinje neuron enough calcium to finally activate PKC. Okay, and now we're reaching the end of the pathway because PKC can phosphorylate targets. Okay, so PKC, this kinase, right, has multiple targets that it can phosphorylate. Right, and one of these targets right, when it's phosphorylated, has the result of reducing the influx of sodium through AMPA receptors. So on the diagram here, right, you can see that long-term depression occurs because now no matter what happens to the release of glutamate from the parallel fiber, right, so this parallel fiber will continue to release glutamate here with the effect of less sodium being able to come in, right? And so reduced inward sodium causes smaller electrical signals. Basically, it reduces the magnitude of these EPSPs. Reduced EPSP magnitude, right, is a form of synaptic depression. Now the stimulus that's the released, right, the glutamate, causes less depolarization, therefore we're less likely to have an action potential. One important point about this is this is localized, okay? So I think we need to maybe write that down. Whoa. What do I mean by localized? So I talked about this diagram up here does a really poor job of, excuse me, of showing the arborization of the Purkinje fibers, right? So this is the Purkinje cell right here. Enormous arborizations, dendritic branches, basically, right? And so this mechanism allows for local LTD, whereas the rest of the Purkinje neuron isn't affected. Okay, so localized LTD occurs in small portions of the dendrites when the parallel fibers are making contact with them. Or excuse me, I said that wrong. Localized LTD exists in small portions of the Purkinje fibers, whereas Purkinje fibers, I'm sorry, I've got myself lost here. Hang on. Oh my gosh, I heard something like I'm here at Lakeland in the basement, you know, at whatever time it is, 9 o'clock or something like that, and I heard steps and like no one should be here. I totally lost my place. So I apologize. What I was trying to get at was the idea that these LTD actions are restricted to a small portion of the Purkinje neuron, whereas EPSPs, right, that's happening throughout the entire dendrite, right? So that's much more widespread. Okay, the final portion of this chapter is what happens to tyrosine hydroxylase. All right, so our third specific example involves tyrosine hydroxylase. And hopefully you remember tyrosine hydroxylase because it was involved in catecholamine synthesis, right? And so to go from DOPA to the neurotransmitter dopamine, right, this was dependent on the enzyme tyrosine hydroxylase, right? So this is biogenic amine, specifically a catecholamine, because we know dopamine is going to be made into norepinephrine and epinephrine. Okay, so this is what we're talking about, but this process only happens when tyrosine hydroxylase is present and phosphorylated. So we're going to talk about how this phosphorylation occurs. I don't have much to say about it, but I think I will start the last video for the day next, and because I don't want to run out of time.